The universe is a vast and mysterious place filled with billions of stars. Each star is a massive ball of gas, held together by its own gravity. Stars are constantly evolving, changing in size, temperature, and brightness over their lifetimes. The life of a star begins in a nebula, a cloud of gas and dust. A nebula is a cloud of gas and dust in space. It can be made up of ionized, neutral, or molecular hydrogen, as well as cosmic dust. Nebulae are often star-forming regions, such as in the Pillars of Creation in the Eagle Nebula. Nebulae can also be the remnants of supernova explosions, such as the Crab Nebula. There are many different types of nebulae, including emission nebulae, reflection nebulae, and dark nebulae. Emission nebulae are clouds of ionized gas that emit light at various wavelengths, while reflection nebulae are clouds of dust that reflect light from nearby stars. Dark nebulae are clouds of dust that are so dense that they block out light from behind them. Nebulae are some of the most beautiful objects in the universe. As the nebula collapses under its own gravity, it heats up and forms a protostar. A protostar is a very young star that is still gathering mass from its parent molecular cloud. This is the earliest phase in the process of stellar evolution, lasting about 500,000 years. During this phase, a contracting cloud of cold and dark interstellar medium, mostly hydrogen gas, collapses under the force of self-gravity, and an opaque, pressure-supported core forms inside the collapsing fragment. The protostar's core has not yet become dense and hot enough for hydrogen nuclei to collide and fuse, forming helium nuclei. The outer surface of a protostar consists at least partially of shocked gas that has fallen from the inner edge of the disk. As the collapse continues, an increasing amount of gas impacts the disk rather than the star, a consequence of angular momentum conservation. Exactly how material in the disk spirals inward onto the protostar is not yet understood, despite a great deal of theoretical effort. This problem is illustrative of the larger issue of accretion disk theory, which plays a role in much of astrophysics. As the protostar grows, it eventually ignites nuclear fusion in its core. Nuclear fusion is a process in which two or more atomic nuclei combine to form a single, heavier nucleus, releasing a large amount of energy in the process. This process is what powers the Sun and other stars, where hydrogen atoms are fused together to form helium. Nuclear fusion is a promising source of energy for the future, as it is a clean and virtually limitless source of energy. However, it is also a challenging process to achieve on Earth, as it requires extremely high temperatures and pressures to initiate and sustain the reaction. This releases a tremendous amount of energy, which is what powers the star. Most stars spend the majority of their lives on the main sequence. A main sequence star is a star in the stable part of its life cycle. They are the most common type of star in the universe, and about 90% of the stars in the universe, including our Sun, are main sequence stars. Main sequence stars fuse hydrogen atoms to form helium atoms in their cores. The process of nuclear fusion produces an outward pressure that balances with the inward pressure caused by gravity, stabilizing the star. The color of a main sequence star is determined by its temperature, with blue stars being the hottest and red stars being the coolest. The main sequence phase of a star's life cycle lasts for about 90% of its lifetime. The length of time a star spends on the main sequence depends on its mass, with more massive stars having shorter lifetimes. This is a period of stable nuclear fusion in the star's core. During this time, the star's temperature and brightness remain relatively constant. As a star ages, it runs out of fuel in its core. This causes the core to collapse and the star to expand. The star becomes a red giant. Red giants are formed when a star like our Sun, or one larger, runs out of its hydrogen fuel. When the hydrogen begins to run out, the inward gravitational forces become less than the outward radiation pressure forces, causing the star to swell and cool, thus turning red. Medium-sized stars expand up to 100 times their original size to become red giants. The outer atmosphere of a red giant is inflated and tenuous, making the radius large and the surface temperature around 5,000 K, 4,700 degrees Celsius. 8,500 degrees Fahrenheit or lower. The appearance of the red giant is from yellow-white to reddish-orange, including the spectral types K and M, sometimes G, but also Class S stars and most carbon stars. Red giants vary in the way by which they generate energy. Most common red giants are stars on the red giant branch RGB that are still fusing hydrogen into helium in a shell surrounding an inert helium core. Red clump stars in the cool half of the horizontal branch, fusing helium into carbon in their cores via the triple alpha process, an asymptotic giant branch AGB, stars with a helium-burning shell outside it to generate carbon, oxygen core, and a hydrogen-burning shell just beyond that. A red giant will usually produce a planetary nebula and become a white dwarf at the end of its life. A white dwarf is a type of star that has exhausted most or all of its nuclear fuel and has collapsed to a very small size. They are composed mostly of electron to generate matter, which is extremely dense. White dwarfs are very hot when they form, but because they have no source of energy, they will gradually cool as they radiate their energy away. This means that their radiation, which initially has a high color temperature, will lessen and redden with time. The nearest known white dwarf is Sirius B, which is located about 8.6 light-years away from Earth. White dwarfs are thought to be the final evolutionary state of stars whose mass is not high enough to become a neutron star or black hole. This includes over 97% of the stars in the Milky Way. After a white dwarf forms, it will gradually cool over billions of years, eventually becoming a cold black dwarf. If a star is massive enough, it will collapse even further after it becomes a white dwarf. This will form a neutron star. A neutron star is the collapsed core of a massive supergiant star, which had a total mass of between 10 and 25 solar masses. Except for black holes, neutron stars are the smallest and densest known class of stellar objects. Neutron stars have a radius on the order of 10 kilometers and a mass of about 1.4 solar masses. They result from the supernova explosion of a massive star, combined with gravitational collapse that compresses the core past white dwarf star density to that of atomic nuclei. Most of the basic models for these objects imply that they are composed almost entirely of neutrons. The electrons and protons present in normal matter combine to produce neutrons at the conditions in a neutron star. Neutron stars are partially supported against further collapse by neutron degeneracy pressure, just as white dwarfs are supported against collapse by electron degeneracy pressure. However, this is not by itself sufficient to hold up an object beyond 0.7 solar masses, and repulsive nuclear forces play a larger role in supporting more massive neutron stars. If the remnant star has a mass exceeding the Tolman-Oppenheimer-Volkoff limit, which ranges from 2.2 to 2.9 solar masses, the combination of degeneracy pressure and nuclear forces is insufficient to support the neutron star, causing it to collapse and form a black hole. Neutron stars are incredibly dense, with a normal-sized matchbox containing neutron star material having a weight of approximately 3 billion tons, the same weight as a 0.5 cubic kilometer chunk of the Earth from Earth's surface. Their magnetic fields are between 10 to the power of 8 and 10 to the power of 15 times stronger than Earth's magnetic field. And the gravitational field at the neutron star's surface is about 2 times 10 to the power of 11 times that of Earth's gravitational field. While newly formed neutron stars can have surface temperatures of 10 million Kelvin or more, neutron stars generate no heat through fusion processes and cool to about 1 million Kelvin when they are between 1,000 and 1 million years old. Still older neutron stars are colder still, such as the well-studied neutron star, RxJ 1856.5-3754, which has an average surface temperature of 434,000 Kelvin. They spin very rapidly and emit powerful radiation. The most massive stars will collapse so completely that they will form a black hole. A black hole is a region of space-time where gravity is so strong that nothing, including light and other electromagnetic waves, has enough energy to escape it. Black holes are formed when massive stars collapse at the end of their life cycle. The boundary of no escape is called the event horizon, although it has a great effect on the fate and circumstances of an object crossing it, it has no locally detectable features according to general relativity. In many ways, a black hole acts like an ideal black body, as it reflects no light. Moreover, quantum field theory in curved space-time predicts that event horizons emit Hawking radiation, with the same spectrum as a black body of a temperature inversely proportional to its mass. This temperature is of the order of billionths of a Kelvin for stellar black holes, making it essentially impossible to observe directly. The presence of a black hole can be inferred through its interaction with other matter and with electromagnetic radiation such as visible light. Any matter that falls onto a black hole can form an external accretion disk heated by friction, forming quasars, some of the brightest objects in the universe. Stars passing too close to a supermassive black hole can be shredded into streamers that shine very brightly before being swallowed. If other stars are orbiting a black hole, their orbits can be used to determine the black hole's mass and location. When a massive star dies, it explodes in a supernova. A supernova is a powerful and luminous explosion of a star, triggered by nuclear fusion or gravitational collapse. There are two main types of supernovae, Type 1 and Type 2. Type 1 supernovae occur when a white dwarf star in a binary system accretes matter from its companion star, causing it to exceed the Chandrasekhar limit and undergo a runaway nuclear fusion reaction that destroys the star. Type 2 supernovae occur when a massive star runs out of fuel and can no longer support its own weight, causing it to collapse and then rebound in a massive explosion. Supernovae are some of the most energetic events in the universe, releasing as much energy in a few weeks as the sun does over its entire lifetime. They can be so bright that they outshine their entire galaxies for a few days or even months. Supernovae are important because they create and distribute heavy elements such as iron, gold, and uranium throughout the universe. They also play a key role in the formation of new stars and galaxies. The remnants of a supernova can form a pulsar or a black hole. A pulsar is a highly magnetized rotating neutron star that emits beams of electromagnetic radiation out of its magnetic poles. Pulsars are formed when a massive star undergoes a supernova explosion and its core collapses into a neutron star. The rapid rotation of the neutron star generates a strong magnetic field, which accelerates charged particles and produces beams of radiation that are emitted from the magnetic poles. These beams of radiation can be observed on Earth as regular pulses of light, hence the name pulsar. Pulsars are incredibly dense, with a mass greater than that of the Sun compressed into a sphere only a few kilometers in diameter. They are also incredibly precise, with some pulsars emitting pulses of radiation with a period accurate to within a millionth of a second. Pulsars are important objects for studying the properties of matter under extreme conditions and for testing theories of gravity. The evolution of stars is a fascinating and complex process. It is responsible for the creation of the elements that make up our planet and our bodies. It is also responsible for the formation of new stars and planetary systems. The stars are our closest neighbors in the cosmos. They are the source of light and heat that make life on Earth possible. By studying the evolution of stars, we can learn more about our own origins and the future of our universe. The universe is a place of wonder and discovery. There is still so much that we don't know about the stars. But with each new observation and discovery, we get closer to understanding the mysteries of the cosmos. Thank you for watching Space Time. We hope you enjoyed learning about the evolution of stars, from their birth in clouds of gas and dust to their explosive deaths as supernovae. We explored the different types of stars, including red giants, white dwarfs, and neutron stars, and learned about the fascinating phenomena of pulsars and black holes. We hope you'll join us again for more exciting adventures in space and time.